So let's look at the problem of constructing a minimum cost spanning tree in a graph. So the first thing we need to define is a tree. So a tree is a graph on n vertices that is has two properties. So it is connected and it is acyclic, that is there are no loops in the graph. So let's look at a couple of examples of trees. So here are two trees. In each of them you can see that the nodes are all connected to each other. From any node you can go to any other node by following a path, and none of them has any cycles. You can't start it in a node and walk around and come back to the same node. On the other hand, let's look at examples of graphs which are not trees. So here are two examples of graphs which are not trees. The graph on the top is not a tree because it has a cycle. These four nodes are connected in a cycle. And the graph in the bottom is not a tree because it is not connected. You cannot get from the left four vertices to the right four vertices because there are no edges between the left and the right. So this is not a connected graph and hence not a tree. So some useful facts about trees. So the first is that any tree with n vertices has exactly n minus 1 edges. Okay, and moreover, this is an if and only if. So any graph that is connected and has n minus 1 edges must be a tree. Okay, so now let's extend this to the notion of a spanning tree. So suppose we have any graph. For example, we could have a graph that looks like this. So this graph is not a tree because it has multiple cycles, but it is connected. A spanning tree consists of choosing some subset of edges so that that subset forms a tree, and moreover it spans the graph. That is, every vertex in the graph is part of that tree. So for instance, we could construct a spanning tree as follows. We could take this edge, then we could take this edge, and then maybe you can take this edge. Then we could take, for instance, so we can't take this edge now because that would form a triangle and that's not a tree. So we could expand our tree in this direction and then expand our tree in this direction and then expand our tree in this direction. So now we have a tree which spans all the vertices, because on the green edges we can go from anywhere to anywhere. The green edges are acyclic, and notice that the original graph has 1, 2, 3, 4, 5, 6, 7 vertices, and there are exactly 6 green edges, which agrees with our characterization above that a tree on n vertices has got exactly n minus 1 edges. Now the spanning tree is not unique. I could take a different spanning tree. For instance, I could start again by choosing this vertex, but now I could instead choose this vertex and then perhaps choose this vertex, right? And then we could extend this and go around this in this direction. And so we have another purple spanning tree which has again 1, 2, 3, 4, 5, 6 edges, right? So a spanning tree is basically a subgraph of an existing graph which connects all the vertices in the form of a tree. So let's look at some typical applications where we might want to find a spanning tree. Okay, so let's assume that Drongo Airlines is losing money, right? So they want to save money by cutting down on some routes, but the license requires that all existing cities remain connected by their network, right? So it is not acceptable to delete routes from the network in such a way that one can no longer go from one city on the old network to another city on the old network, because there is no way to go from one to the other. So in such a situation, you would like to cancel some flights but retain a spanning tree, right? So this is one typical example where now you will take the original route map of Drongo Airlines. Think of it as a graph, right? You connect any two cities by an edge if there is a flight between those two cities, and then you identify some spanning tree and say we will retain the flights on this spanning tree and we will remove all the other flights and we will not violate the terms of the license. So here is another possible example. So supposing we have a highway upgrade proposal. Okay. So the government has promised to connect all major cities by, say, an 8-lane highway. Okay. Now the elections are coming up and the government has to make good on this promise. Okay, so the plan is, of course, to upgrade some existing highways. Now if one reads the proposal naively, you would expect that every existing highway between two major cities should be upgraded to 8 lanes. But if funds are short, it suffices to upgrade a spanning tree, right? Because if we upgrade a set of highways that form a spanning tree between these major cities, then you can go from any city to any other city by an 8-lane highway, and that's all the government has promised. The government has only promised to connect all major cities by 8-lane highways, not to directly connect all major cities by 8-lane highways. So these are two typical examples where you would like to look for a spanning tree from an underlying graph. Now we can add one more variable to the equation. So we can add costs to edges, right? So the cost could be a real cost. So for the flights, for instance, it could be the fuel cost on a sector. Okay. For the highways, for example, it could be the length of the highway, assuming that upgrading a highway section is proportional to the length of the section. It takes more money to upgrade a 100-kilometer section than to upgrade a 20-kilometer section. So now we had costs. So now each spanning tree, there is an associated total cost, right? So you take the edges that form the spanning tree and add up the cost, and that is the cost of the spanning tree. And in both these examples and in general, the typical requirement is to find a minimum cost spanning tree, right? So Drongo Airlines would like to retain those flights which connect all the cities such that the fuel cost to operate these flights is minimized. So this involves constructing a minimum cost spanning tree over the existing network. Similarly, the government would like to upgrade highways between the major towns so that you have 8-lane highways connecting all the cities, but the cost of achieving this is minimized, and therefore they would look for the shortest total length of all these connecting highways. So one thing to note is that we saw that there could be many spanning trees in general, and we are looking for a minimum cost spanning tree. So is there always going to be a unique minimum cost spanning tree? Well, the answer unfortunately is no, because we could have trees in which different edges have the same cost. Suppose, for example, this is our graph. We have a graph which is basically a square, 4 vertices connected in a cycle, and we have two opposite edges with cost 5 and two opposite edges with cost 3. Now, a little bit of inspection tells us that we could construct a minimum spanning tree by taking the top cross edge and the two side edges, and this would give us a total cost of 3 plus 5 plus 3, which is 11. On the other hand, we could swap the top and the bottom edge and construct a different spanning tree which takes these three edges, and again the cost is 3 plus 5 plus 3 is 11. Now notice that if you took a spanning tree which takes the side, for example, if you do a spanning tree like this, then you would have a cost of 5, 3 and 5, and so your cost will go up to 13. So this is not a minimum cost spanning tree. But among the two minimum cost spanning trees, they are quite different. I mean, they have different edges, and this is a feature that arises because we have these multiple cost edges, multiple edges of the same cost. So we have two 5s and two 3s. Right? So in fact, you can actually argue that if the costs are unique, that is, no two edges have the same cost, there is only one minimum cost spanning tree. But in general, we should keep in mind that the minimum cost spanning tree is not unique. So there is a natural greedy strategy that one can think of, given that wants to minimize the cost. Okay, and the greedy strategy is to examine edges in increasing order of cost. Right? And what we would like to do is we would build a tree using lower cost edges in preference to higher cost edges. Right? So this is the natural greedy strategy. We have a notion of cost associated with our tree, and so we go in increasing order of cost because we are looking for something which is of minimum cost. Now, exactly how to implement this strategy is not clear, and it will turn out that there are at least two natural ways to do this, and this will give us two very common algorithms for this. One algorithm is due to Prim, it's called Prim's algorithm, and the other one is due to Kruskal, and it's called Kruskal's algorithm, and we will see both these algorithms in detail later on.